Hi, my name is Lobel Danicic and I'm in Digital Rock Physics team at Math to Market. In this webinar, we'll focus on one application field of digital rock physics, which is prediction of geomechanical properties. We will focus on some key insights for successful workflows, what are also common challenges in experiments and in numerical predictions, and we'll go through the workflow showing what actually comprises the digital rock physics approach for geomechanics, where you predict the rock's properties directly from micro CT scans. And then we'll move forward with a few different simulation setups in GeoDict, showing how to effectively predict rock elasticity and stress-strain curves. So, first, knowing geomechanics is crucial both for reservoir properties prediction and optimization of production, but also for the operational safety and, for instance, wellbore stability. There are, however, different both experimental and numerical challenges when you want to get those geomechanical properties and also understand what's actually occurring in the rock minerals and pores during the deformation and mineral failure. So one question is often raised, which is how to actually gain more insights and predict rock mechanics. So see what actually goes and understand how this could be extrapolated to reservoir production. One, let's say, hypothesis is that digital rock physics definitely helps with the understanding and visualization of such processes, showing the rock deformation taking place in 3D and efficiently predicting both the elasticity and stress-strain curves and their mineral failure. So in this webinar, we will focus on some key insights for successful workflows, what are also common challenges in experiments and in numerical predictions. And we'll go through the workflow showing what actually comprises the digital rock physics approach for geomechanics, where you predict the rock's properties directly from micro CT scans. And then we'll move forward with a few different simulation setups in GeoDict, showing how to effectively predict rock elasticity and stress-strain curves. Also, we had some questions raised and they will be answered after the session. First of all, going back to the motivation behind why prediction of geomechanics and rock mechanics properties is important, let's start with the production. You're producing oil or gas, and due to the pressure drop, you have a change in the effective stress state in your reservoir. This can highly affect the pore throats, coming to the pore collapse, and in the end affecting the productivity of the formation. Same can happen also during the injection, where, for example, you have the pore pressure increase, and there may come to the failure of rock in a way to fracturing. So this is quite important from both operational side and safety as well. Second application of knowing rocks' mechanical properties comes from the seismic monitoring, where the rock elasticity is a link between the seismic waves you measure and the situation going on in the reservoir, meaning, for example, the change in the fluid saturations and how, for example, plume migration during CO2 injection is occurring in real time. Furthermore, one also application of knowing of geomechanical properties is regarding the hydraulic fracturing, where you directly have to know the rock's strength, its failure stress state, and that it helps to effectively predict when will the rock fail, and how will the fracture propagate. So all of those are some quite important questions to be resolved, and there it is why geomechanics help. So some key properties for this are Young's modulus, Poisson ratio, and bulk modulus. I'm sure most of you are aware of. And there is the complete stress-strain response, including both the rock's failure in the non-elastic regime and, for example, sometimes also plastic or viscose plastic deformation. Also, there is the P and S waves, or the acoustic velocities, that, as mentioned, are related to seismics and interpretation of fluid saturations in the rock. So I'd like to tackle now some challenges in obtaining the geomechanical properties. And we'll start with experiments and the experimental setups. Here on the right side, you can see such setup for the triaxial testing of rock samples, where you have many different parts, and they include quite complex configurations of pressure valves, the inducers, the stress load in the Z action, and also confinement. And all these parts require quite delicate handling by experts and require lots of time, so meaning in the end the resources. Also, the sample themselves, they have to be of specific shape and size, being cylindrical and often with a diameter of either 1.5 inch or 2 inches to actually fit into the system in the previous slide. What's also one thing is that you're testing for rock's strength most of the time. So you're basically compressing the rock until it's destroyed, until it fails. So afterwards you lose that sample. And we all know that actual core samples are quite precious, and each one of them is very important. So just knowing all of that, I can say that digital rock physics can tackle all of those issues and doesn't have them, but there are some other challenges which I'll briefly tackle in a moment. So I would say the first challenge with digital rock physics is the micro CT resolution of the scan and some direct segmentation issues, like how much of porosity you manage to capture, and are there some micropores or grains or minerals that are not properly resolved in your rock model from micro CT scans. So to give you an example, here I show for the same sample, if you have the, for example, low resolution scan, there you will have the mineral grains and the pores less well resolved, and the grains will appear to have much larger contact area between them, and this affects the stiffness prediction. Most of the time you would have the effect of overestimation of rock stiffness. On the other hand, if you have the same sample but imaged with higher resolution, those contact areas between the grains are now clearly seen as much smaller, and in the end the stiffness will be more precisely predicted, showing lower values. There is also one big topic, which is how can the rock samples match the physical reservoir scale, and this is something that I would say is valid both for experiments and also for digital rocks. In terms of the digital rocks, there is one more scale lower in the size, and therefore representative elementary volume is even more important. So to give you an overview how what I mean by that is, if you say have a large core with a few different plugs, you need to make sure that the plugs you take out and on which you do the prediction of the stiffness, for example, that those plugs are representative and that in the end you can upscale those results to core scale mechanics. There are different approaches for tackling the heterogeneity and upscaling of stiffness, one of them also from the Stanford University group. Now, there is another question, and that is, how do the results from the simulations match with physical reality and the experiments? So, oftentimes, this question is raised, and it may require some modeling of the stiffness of the rock matrix. For example, what I mentioned earlier, when you have a resolution that doesn't properly capture all the micropores in your sample, then you need to make sure that those micropores in a way shall affect the stiffness, and the stiffness of the mineral should be lower. So there is still some calibration for the digital rocks, which then can be used for future for predictive purposes. Now, when it comes to the actual workflow in the prediction of geomechanics from digital rock physics, it all starts with the imaging. So you take your plug and you scan it, for example, in micro CT device, and the result is the grayscale image. With this grayscale image, you create the 3D digital rock model, which has dedicated separated pores and different rock minerals within the model. On this model, you can now predict both rock's elasticity as well as the strain stress curves and also the acoustic velocities, for example. So with that said, let's now jump directly in GeoDict, and we'll show the workflows for effective stiffness prediction and compare it with one approach where you directly identify those grain contacts, which, as mentioned, definitely impact the stiffness and rock strength. We'll also show the results from the acoustic velocities computation and show setups for getting the complete stress strain curve together with the mineral failure. What we will use in this webinar is the Gildehauser sandstone, the one from Stefan Berg publication. And here the sample has approximately 20% porosity and 1.5 Darcy absolute permeability. The voxel resolution is around 4.4 microns, and the crop dimensions we will use in the webinar are 256, and 400. So first of all, let's start by opening our structure, and with that we can then start the prediction for the stiffness. So here we have our rock sample. And to start with the setup for the effective stiffness, we go under the predict menu on top and then select ElastoDict. You here have also the description saying it's the module for mechanical rock properties and large deformations. So now we will go with prediction of rock elasticity, which is available here under the ElastoDict sub-module menu under the effective stiffness. Let's click on Edit, and in the window we will be able to set different parameters for the simulation. In the first tab, called Constituent Materials, we can see the two phases that are at the moment present in the rock, which are water and the quartz for the gray solid phase. What we can do here is also select different material within the domain. For example, if we click on water, we could now select different fluid like air, carbon dioxide, and so on. Same goes with the quartz, where in our material database we already have some different minerals like calcite, dolomite, or even some clays like iolite. For now, let's go with quartz. Here there is the material law section where you can actually change how the both fluid or solid will behave. If we go with the material law called pore, the water will be considered as having no effect on stiffness, meaning it would be like the rock is dry or effectively empty of any fluid. If we select the compressible fluid mode, then we can see the change in the rock, in the water stiffness. So in this case, the bulk modulus. This we can see by clicking the view button on the right side. And here we see the water bulk modulus, which corresponds to approximately 2.07 gigapascals. There's also the option to include the thermal expansion of the brine, and this I'll also explain in a moment. When it comes to the mineral phase, there is also option to use elastic or anisotropic tensor. So you would be effectively able to use different elasticity values in different directions. With that said, we can move on to the next tab, which is the load case. So if you want to get the complete stiffness tensor, meaning in all directions, you simply select the first option, by default, the stiffness tensor. Otherwise, you could also go and select to compute in one of other directions. Then, regarding the load type, you can either go with strain or stress, where strain will be effectively deforming the rock sample, while stress first of all starts with the pressure and then predicts the strain. So both strain and stress, in the end, the value you put in won't affect the predicted stiffness, as the Hooke's law formulation in the solver is set in linearly. So there is only the scale of strain or stress field. If you would like to see the actual effect the rock's deformation has on the stiffness, we would use the deformations module, which we'll also show a bit later. So for now, we can go with strain, and this is usually the recommendation, as then solver directly has the deformation that it will apply, rather having to iterate from the stress state towards strain. Regarding the load case, if you go with the complete stiffness tensor, we highly recommend to compute load in all the directions and all the planes, as this will make sure that you have all the necessary parts of the tensor for effective prediction of stiffness. When it comes to the boundary conditions, you can either go with periodic or symmetric, and here we recommend to go with symmetric for rocks. Now, there is some effect, and you may see it as the boundary, so meaning there is like perhaps some artifact that can come if you select for rocks, which we know are not periodic structures. If you select the periodic effect, on the very edge of the domain of the structure, you could see some minor artifacts with stress or strains. I also mentioned there is option to include the thermal expansion, where you can see the effect that increased temperature would have on the stiffness of your structure. For now, we can turn this option off. The next step is solver, where we have two different solvers, FieldMat and our in-house solver Lear. And I'll quickly go through some of the settings for example, FieldMat solver. So the first part shows the stopping criterion, meaning what will control the end of the simulation. For the most part, what you need is the tolerance, and this is basically showing how small the error should be relative to the previous iteration steps before the simulation stops. You can also select and go with the number of iterations of maximal runtime of the simulation. Then, when it comes to the equivalence principle, this is the approach that is used for actually homogenizing the effective stiffness for the complete equivalent structure to your structure that you have loaded. There are two approaches. One of them called strain, and other the energy and strain, where there are perhaps some minor differences in the end, but for the most part the strain equivalence is what you can start with. Also, there is the a selection of the iterative method for the solver, and you can either go if you have the stronger machine, stronger workstation with more RAM memory, you can go with fast, or if not, then go with intermediate or memory efficient method for iterations. Then there is also the option for the setup of downsampling, where this is basically effectively reducing the number of voxels by merging them into one. For example, two voxels in each direction would become one voxel in the end. This, of course, speeds up the simulation, as there is many less voxels than before present in the complete structure. However, it also brings in some potential errors, as you're effectively reducing information in your domain. For now, we always recommend to not use it if not highly necessary. Now, next step is output, where you have different possible fields that can be written out as the result, and they include displacement in X, Y, or Z directions. And also for the stress and strain fields, you can export them in X, Y, and Z, and also different planes that are available. By default, the export is set to go with von Mises stress and strain fields, which basically homogenize the different directions for the complete structure. Also, just a brief note, you can also have the decomposition of the stiffness according to the principal material axis approach, where you would have the option to see the highest stress and the deviation from it in the specific direction, and also see, for example, the change of the stress in different planes. You can keep the default options here. And in the final tab, there are the equations that are used in the numerical solver, and also the references and papers which utilized and developed the solvers used here. Let's click on OK, and now you could click Run, where I will directly open the results. So, depending on the sample size, you can have from a few minutes up to a few hours the simulations. And in this case, I think simulations took around 1 hour. Let's click on File and Open Results. And there I have the results from the effective stiffness. So now we have our predictions, and we can have the results such as the Young's modulus seen, as well as the Poisson ratio, and also the cubic and orthotropic approximations. Now, what I mentioned earlier, there are also the decompositions by principal material axis, where you can see even more details on each of the approximation approaches for different considerations of material properties. Probably what is more interesting and visually appealing is to actually see the stress and strain fields. So let's go to the strain and stress visualization tab. Here we can have the option to visualize the strain and stress in different directions, different planes, and let's go with the Z direction. So we select the direction we want and click on load. Now we are also asked, do we want to visualize both von Mises strain and stress fields, and we click on OK. We want to load both of them. And we want to keep our structure visualized. So let's now move into the main screen where we have our 3D rock model. And for a moment, let's turn it off. So by clicking here on this check mark, and let's go to the volume field tab. So here we see our von Mises strain field, and we can even modify the volume field legend to actually have a bit more clarity and higher contrast of the colors. So to do so, click here on the edit button in the top left corner. We can also then manually change the range, for example, by doing the manual range and perhaps moving the slider a little bit. The results are effectively only visualized changed, so there is no change in the actual field. It's just the scaling of the colors of the visualized range. And here now we see the von Mises strain field, and if we zoom in a little bit, we can start noticing that well, from what it seems, the strain is concentrated around the contact angles, around the contacts between different grains in the structure. We can see this again by turning on our 3D model, and here you can see definitely some grains, and if we turn them off again for a moment, we can notice that there is definitely some strain concentration around the edges of the grains. So what this means is that there should be for sure quite high effect of the grain contacts, and we will go into understanding this in more details with the structure that actually has the determined grain contacts in the domain. At this moment, I should note that current structure has only the pores and one solid phase determined, so there are no explicit grain contacts already in the structure. With that said, we can also visualize the von Mises stress field, and first of all we can move the volume field legend back to the default setting, which is using the percentiles. Let's close this window and change to von Mises stress. So now by seeing the von Mises stress field, this gives even a better view into where the highest stress is present. And if we turn on the structure again for a moment, we definitely see that this is occurring for the most part near the grain boundaries, so at the grain-to-grain contact areas. Now, with that, we can go and show how to create the structure that has the grain contacts inside, and from this we can then predict the stiffness of this sample. To do so, let's click on the GeoApp menu on top, and then Digital Rock Physics, and here select Quantitative Seismic. And here we can go and click on Edit. So this whole workflow would effectively predict not only the structure with the grain contacts, but also the rock's elastic properties, as well as the calculations of P and S waves and other necessary values for the quantitative seismic interpretation. Now we want to focus only on this contact correction method, which is the bottom part, where we have two different methods available for actually determining and factoring the stiffness of those grain contacts. Let me show you a visual illustration of both approaches, so to give you a bit better understanding what's behind them. First approach is called the grain contact factorization, where, for example, let's say you had three different minerals, so not only quartz, but maybe quartz, feldspar, and micrite perhaps, and each of those minerals has different stiffness. Their contacts would be then factorized both on the area and the mineral that is at this border, and also the reduction factor applied generally, globally for the whole structure. So here is the 2D slice of the same structure, where you would have three different minerals in green, red, and yellow. And there are also now the contacts identified, and each contact is factorized based both on the area as well as the mineral properties and also the reduction factor. Now there is the other approach called explicit in the quantitative seismic GeoApp, and this approach is slightly different. So let's say that you have your structure with only pores and the grains, let's say one solid mineral phase, and here the watershed algorithm identifies the grains and their boundaries, and then there are those contact areas present. Now in the next step, those contact areas between grains are eroded, which effectively means their surface is reduced by a certain number of voxels. The amount of voxels is part of the user input, and I'll show how to set it up in a moment. This in the end doesn't change the stiffness of those surfaces, but reduces their area, which will also reduce the total sample stiffness and strength. Okay, with that said, let's go back to GeoDict. And here, if we select, for example, explicit method, you would have the number of voxels you can erode for those grain to grain contacts. And by clicking OK and then run, we would first have the new structure created, and then its stiffness and acoustic velocities would be predicted. Now let me directly open the structure with such settings, and also with the results from the effective stiffness computation. Let's click on File and then Open Results, and then here there is the results. First of all, let me load the structure from this computation of effective stiffness. And now you can see the structure, so the same one as before, but now with identified grain-to-grain contacts. Here is also the undo button, which basically loads the previous structure. And this can be done to compare between the two structures. So you see where those grain-to-grain contacts are identified. And now we can go back into the results and see the effect the grain contacts had on the Young's models. So in GeoDict, you can both zoom into the results by, for example, clicking Control button and holding it, and then scrolling your mouse button. And if you hold Control or Shift and click on multiple result files, you can open them simultaneously. We can also do a bit of zoom in into the first results. And now we can see that there is a considerable effect of the identified grain contacts and their reduced areas on the predicted Young's modulus of the sample. So from the initial case where we had no contacts, there was around 49 gigapascals Young modulus, and now it dropped to 41.5. So we can also do the visualization of stress and strain fields for the second result, and then see what's the concentration of strain and stress fields in this structure. Let's quickly turn off the structure for a moment. And yes, here if we go to the volume field, we can first see that we have loaded the von Mises strain, and it is even more visible that the strain is directly occurring near the contact areas between different grains. We can also see the stress field, and this gives an even better picture of where the most of the stress will be concentrated. So we discussed how to utilize quantitative seismic interpretation GeoApp for creating the structure with identified grain contacts, like this one here. And now let's go into more details on actually applying this GeoApp and how it's set up. So let's go to the GeoApp menu once again, and here clicking on the digital rock physics, select quantitative seismic. Click on edit button, and here we have the option to predict QSI either on the current structure, or there is also the option to use folder of structures. So what this effectively means is, let's say you have the simulations with different brine and gas saturations, for example. You could be able to provide a folder containing all the different samples with different saturation levels, and then the QSI GeoApp would predict the acoustic velocities for each of those saturation steps within the sample. Now we want to predict only on the current structure, and again let's utilize the symmetric boundary conditions and compute in all directions. For the method used, you can use, as we discussed, either the explicit or the area dependent grain factorization method. By clicking on OK and run, we would then get the results. Now let's open the results. And here is the report that you get when you predict the QSI. So here you get effectively a range of porosities, densities, P and S wave velocities, and so on for each of the structure you used in the simulation. As in this case, we used only one structure. We get only one data point, which is also reflected here in the plots, where we only have one point for the VP and versus bulk density cross plot. Now, if you had run the simulation on different structures, then you would have this range quite diverse, and also in the plot it will be reflected with having different predicted relations between each structure's VP and the density. We can also open the results from particularly this intermediate step, and here you see once again only the results for this structure that has been predicted. With that said, let's move further with the setup of the deformations or the complete stress strain curves, including mineral failure. To do so, we can go to the predict option here in the top menu, and then click on ElastoDict, and from here select the deformations. Clicking on edit button we will get different options, where some of them will be quite similar to what we previously have seen within the effective stiffness setup. We can expand this window, and from there then parameterize the materials present in the current structure. So now we have the water brine currently with the low as it's the empty pore, and then there is the quartz phase as well as the grain contacts which have the properties of quartz. So let me show you now how to turn on the failure for each of the mineral phases, so both the quartz and the grain contacts. First, I'll quickly just move from quartz to manual material, which will allow me to edit also this phase by going here to the rightmost corner, where we have the option to edit each of the minerals. Let's first click for the quartz on the edit button, and here there are different deformation lows available. So if we go with the failure model, by clicking on this button and selecting failure stress, we can put in the failure for the quartz phase. From the literature references, authors there determined that the value for the quartz, pure quartz failure is around 2.3 gigapascals. So let's go with that value here and click on OK. For the quartz grain contacts, again, let's click on Edit, and then there is again the same procedure of selecting failure stress and then putting in the value. So if the pure quartz has around 2.3 gigapascals, we can still argue that grain contacts are perhaps not 100% properly resolved in the micro CT scans, and that their failure stress should be lower. So let's go with value of 1 gigapascal here. Click on OK. In case you don't see this check mark turned on here under the failure column, make sure to turn it on to have your failure stress actually considered for the stress strain curve computation. With that said, we can go to the load case tab, and here by default the setup of the experiment is like for the uniaxial compression, so to obtain the UCS of the sample. You can go with either the strain, which is path controlled, or stress, which is the force controlled option. And path controlled works faster, as again the structure is first deformed and then you compute the stress field. And if we were going with the stress field, there would have to be some iterations to reach the exact strain for that stress. We can also go and, for example, turn on the confinement, or also the pressure within the pores of the sample. But for now, let's keep those options turned off, as we want to compute and predict the uniaxial compression. Here in the bottom part, we can further set the simulation parameters, like what would be the maximum magnitude of the strain. And here we can select, for example, 1%, and also say in what number of steps we want to reach that result. The number of computation steps will affect how long the simulation takes, so bear that in mind when you're setting up your own stress strain curve simulations. We still need to click apply, and now we can see that there has been a change in the load table here on the left side. We could now either save this load table, and then this could be used for the future in the next simulations. You can also load, of course, then the table from the before, so same process. If we change to load graph, Here we see what would be the load in time. So with the increasing time, how many steps, we have the also increase in the strain field, and that's a good way how to see what type of load you're having in your sample. Again, the boundary conditions are quite important, and although the symmetric ones usually take longer for computations, they are also more precise and avoid having some larger artifacts on the edges of the structure. So let's go into the next step, which is geometry handling. And here there are two options for deformation type. For rocks, we always recommend to go with the option without geometric nonlinearity, which means that there is no large deformation of many percents occurring, which is perhaps for some other types of materials like foams or some others. So for rocks, let's go without geometric nonlinearity. Then there is also the option to calculate on deformed geometry, which effectively means that you would take one structure, one initial structure, deform it, and then use this deformed structure for the next steps. So if you have very small deformations, this is not really needed and may even lead to some, let's say, errors. Namely, so between each of those deformation steps, the structure has to be resampled to be, let's say, adapted for the new stress and strain fields and how they impacted the material within the domain. And that requires the resampling procedure. And if the strain is very small, you can have an effect on this resampling where you don't effectively get the material that should be in place before. So for small deformations, like in this case, we can turn it off and continue with the simulation setup. Regarding solver tab, we discussed it in the setup of effective stiffness, where we have the stopping criterion and also selection of different iterative methods. And again, there is the option to use the downsampling, which we do not recommend for rocks at least. Now, under the output, there are different options. Again, quite similar as within the effective stiffness. And there is one extra option, which is to write out the deformed geometries. So from each applied stress and strain field, if you select this option, you would also get the structure, the digital rock model, which has been deformed at that particular strain and stress. This, if you have a very large structure, can take quite some time and disk space. So I just want to make a note that this can in the end impact your runtime of simulation. But let's keep this option turned on, as it's also quite good to see how the deformation is occurring in your sample. And we can click on OK and then click on Run here. I'll open directly the results, and from those results we can analyze the stress and strain fields. So here we have the results table for both for strain and for stress, but I know that this is quite overwhelming, so to say. So let's go to the plot visualization. So here, by clicking on the plot sub-tab, we can go and see the compressive stress in Z direction versus the strain in Z direction. We see that there was the failure of rock at approximately 0.08 gigapascals, and afterwards still some compression occurring and additional failure in the rock. Now we can also visualize, for example, one of those steps with the both strain, stress, and failure fields for each of the minerals. Let's perhaps go with one intermediate step and click on the load of the form geometry as well as the stress and strain fields. Click on OK, and let's go to the main window. And here we have our deformed structure, and we can now go into the volume field tab and, for example, observe the strain and also the stress fields. So, for example, if we go back to the strain field, we can see the concentration definitely occurring near the grain contact areas, and this is a high indicator of the effect they have on total strain and stress present in the structure. Now, if we go and want to also see the failure occurring in both the quartz or the quartz contacts, we can turn on the failure 1 for the quartz phase and see the actual failure spots in the lighter blue shade here. We could also turn off the visualization in the grain contacts, so just to have the visualization in the quartz. And we can see that most of the failure actually occurred in the top part near the edges where I assume there have been different grain contacts identified, yes. So with that said, we can also visualize the failure within the grain contacts and see that they are at the top part, but also some parts lower in the domain. And we could even turn on the transparency to see this more clearly. Let's turn on the visualization of the grain contact failure. And now we can see it more clearly, also with the transparency mode turned on. With that said, we can now go and see the setup for the deformation of the sample, including the confinement, where we'll go into the deformation setup and actually see that there is only one minor difference, and that is in the load case. We always recommend to also provide the adequate names for each of the result files so that you make sure to later differentiate between the age of the simulations and not have any overwriting of the result files. Let's go to microscopic load case here, and in the experiment conditions we can now select the confined, and this is the only setting that would change. By clicking OK and then clicking Run, we could predict the deformation where there is confinement, meaning there is no X and Y the strain possible and a deformation of this rock. Now let's go and open the results and see the effect that confinement has on the rock's failure. So if we again go to the plots tab and then open multiple results, so the same strain stress curve on the same structure but without confinement and with confinement, we can now see that there has been some effect with increase of the failure stress with confinement turned on here in the right side. This is effectively what we would expect, where by having confinement, rock appears stiffer and having a larger failure stress than without the confinement. And with that said, we can now move towards the questions that have been raised throughout the webinar. We had different questions, and now let's answer them. So one of the questions was, is it possible to define a custom material with anisotropic properties? And the answer is yes. So by quickly showing under the constituent materials tab, you can define the anisotropic properties by selecting a different anisotropic law, and then have the different set of the elasticities in each direction. Then there is the question, can this tool be used on non-woven materials, such as those used in oil filtration? So yes, the GeoDict can be used for non-woven materials too, and I think more details on that can be provided by my colleagues from the digital materials team, and they, I think, also had the webinars on this topic. There is another question regarding the formulations which are used here for the measurement of the effective stiffness, especially in anisotropic and inhomogeneous media. So I would say that the formulation and approach utilized here in GeoDict is called linear elasticity, which effectively considers your rock structure, your domain, as having different elasticities in each of the materials. And then it targets the effective bulk property for the equivalent material of virtually having a homogenized stiffness. So this is done with a number of steps where you have the strain and stress fields applied, and for each strain then there is the measurement of error between what would be the homogenized version and what the current response is in the heterogeneous structure. There is also the question, how did you incorporate this parameter of anisotropic modeling, also considering different saturations in multiphase fluids and different fracture densities and orientations? So to answer this question, one part is that you can also include the anisotropy within the, for example, effective stiffness computation, what we previously showed. And there is also the effect of the different fluids where if they are considered as compressible fluids, they will have the impact on the predicted effective stiffness. In GeoDict, there are no dynamic fluid movements that would affect the predicted stiffness, so the method could be considered more quasi-static in that sense. Now, there is a question related to if, for example, there is the measured complete stress strain curve from the geomechanical test, and then there is the in situ micro CT monitoring, for example, with a Deben cell, and whether the results from the experiment can be used in GeoDict to further characterize the mechanical properties of rock samples. Indeed, so this is possible, and today we haven't shown it in the webinar, as this would be a bit more details. but there is the option to actually parameterize your own models, your own material laws, and use the optimization so to actually match what you also saw in the experiments and what you got then from the stress strain curve there. So this is possible as well. Now let's see other questions. So there is the question, can the software model the fluid effect on the acoustic and geomechanical properties? And can you evaluate the uncertainty when modeling failure? To the first question on the fluid effect, as mentioned, we can model the fluids as compressible fluids, where they have their own bulk moduli in the structure. That's possible, and you would definitely notice the effect on both the stiffness as well as the P and S waves, acoustic impedance, and so on. There is no dynamic effect like the squirt flow and the interface change between the fluids. For example, what is observed in the field, and we have the quasi-static approach as previously mentioned. Regarding the question on the uncertainty when modeling failure, so in GeoDict, it's quite easy to set up the failure deformation simulation. And what could be done is to provide the range of different failures and see what's the effect on the predicted stress strain curve. So this can be done and also quite well automated with perhaps either the macro or dedicated Python script. Another question, is it possible to model a new created fracture during deformation and also crack fracture propagation for different applied stress? Yes, so as shown in the setup of the stress strain curve simulation, it's possible to set a different range of the stresses applied or strains applied and how they affect the rock failure and creation of the crack. So in a way, you can directly observe that and see also, for example, if you do the load and unload sequences, what would be the effect on the failure and the fracture that has been created. So with that, that was our final question. And once again, thank you all for taking your time and watching this webinar. And now I would like to tackle some next steps. So if you'd like to get into more details on your geomechanical workflows, particularly with the digital rock physics, feel free to reach out and either book a one-on-one meeting or just ping us an email. You can also apply for the GeoDict evaluation and get the 2-week trial license. And also one thing is that we can discuss and you can send us your data set and we will do the brief analysis and let's go into further discussion for that. So thanks, and with that said, I'll wrap up today's webinar. Bye.